So predicting the type of radioactivity. There's probably a lot of questions going through your head. Why does this happen? Why are nuclides radioactive? Some nuclides are, some are not. Why do they undergo different types of decay? Lots and lots of questions. So a nucleus is a collection of protons and neutrons, and because we got tired of saying protons and neutrons all the time, we call those collectively nucleons. So these are the particles in the nucleus, the nucleons. And those are held together by something called the strong force. That is its name, its official name, the strong force. This is a fundamental force of physics that acts on very, very short distances. So you may have wondered, and then just kind of gotten over it, how can a nucleus exist with all these positive protons all packed in next to each other? I thought like charges repelled each other, right? The electrons are out doing their wave thing and spin paired and stuff, and they've got space. But those protons are smashed together. How does that even work? Well, the strong force has something to do with that. So we do have this repulsive Coulombic. That doesn't sound right. Repulsive electrostatic force between the protons because of their positive charges. So that's repelling them, but then we have the attractive strong force that occurs between all nucleons. So a proton and a neutron, two neutrons, two protons, there's this strong force that attracts them. So we've got a balance between attractive and repulsive forces. And it's that balance that determines whether a nucleus is stable or not. So the neutrons are important in stabilizing the nucleus because they will attract other nucleons without contributing to any repulsive forces. So if you just had a bunch of protons, it would not be stable. And that's why for everything above hydrogen, hydrogen only has one proton, so there's no issue with stability there. But you look at helium, the next biggest, it's got 2 electrons. It also has 2 neutrons in the nucleus. Without that, it's not stable. So the neutrons sort of act as glue. So we've got, gotta read this. Due to the energy levels occupied by nucleons, a point is reached where the energy payback from the strong force no longer compensates for the high energy state that added neutrons must occupy. So there are energy levels among the nucleons. Thankfully, we don't need to talk about what they are or anything like that, but there are levels. And so you can't just add an infinite number of neutrons and expect them all to stick together, because the ones that are coming in are going to occupy higher energy levels. You can think of it a little bit like Bohr's model of the atom. Whereas you're adding additional electrons, they're higher in energy. So what we observe is that the ratio of neutrons to protons, symbolized as N over Z, is important in determining nuclear stability. So if we plot number of neutrons on the y-axis versus number of protons on the x-axis, we can, we've got green dots that are representing stable nuclei and yellow dots that are representing unstable nuclei. And so this area in the center where the green is called the valley of stability. So, you first look at this and you're like, how is that a valley? Well, think of the yellow on each side as being mountain ranges, where the energy is higher, it's unstable, and down in the middle along this line, maybe there was a river running through there or something, those are the ones that are stable. It's called the valley of stability. So the stable ratio is not always the same. That'd be just too easy, wouldn't it? Oh, we need a ratio of 1:1 and it'll be stable. No, it keeps changing. For the smaller elements, the stable ratio is 1:1. So here we've got carbon 12 is a stable element. Stable isotope of carbon. 6 protons, 6 neutrons. Its ratio is 1. It is stable. So this is the line where N over Z is 1. We see that as we increase in size of the atom, the ratio that is stable increases. So we get up here to mercury, and the stable ratio is 1.5. When you get past 83 protons, there are no stable nuclei. There are not. So bismuth is the largest atom that has a stable nucleus. The type of radiation that's emitted depends partially on this ratio. So what we can predict is that emission or electron capture will occur on these unstable nuclei in a way that will cause their N to Z ratio to move towards the stable, right? So things over in this area are going to do something where the number of protons decreases, or conversely, where the number of neutrons increases. So if the N to Z ratio is too high, that means we've got too many neutrons, and those are going to tend to decay in a way that neutrons get converted to protons, and that's typically by beta decay. If the N to Z ratio is too low, that means we've got too many protons. They'll tend to convert protons to neutrons, and that could happen either by positron emission or electron capture. Alpha decay also raises the N to Z ratio, but the effect is smaller. So can we absolutely predict what type of radiation is going to occur? No. No, you can't. But there are these generalities. So in attempting to predict the type of radioactivity, we can look at figure 20.5, the valley of stability, and see, well, what needs to happen in order to make that ratio closer to the stable one? Well, what if you don't have that graph handy? You can compare the mass number of the nuclide to the atomic mass listed in the periodic table. So let's look at ruthenium. So ruthenium, where'd you go? I lost ruthenium. There it is. I was looking too far down. Element number 44. So ruthenium on the periodic table has an atomic mass of 101.07. That is the average of the naturally occurring isotopes of ruthenium. If we have a stable isotope of ruthenium, its mass number is going to be very close to the mass number of the average, okay? And so we can compare this mass number. So 112 is higher. That means more neutrons. So in order for this mass number to get closer to this, we need to lose neutrons. So then we're going to predict beta decay. Make sense? So predict whether each nuclide is more likely to decay via beta decay or positron emission. So before we even start looking at that, let's remind ourselves what beta decay and positron emission are. So beta decay is when we lose an electron. Positron emission is when we lose a positron, the anti-electron. When we lose an electron, the atomic number changes, right? The atomic number changes, the mass number does not change. So what happens, I'm trying to reason this through in my head and it's sticking. We had, a proton turning into a neutron and an electron. Nope. Yep, backwards. So writing out these little equations can be super helpful. So I need a 1 here and a 1 there. And then this will be 1 and 0 over here. So that's a neutron, this is proton. So beta decay, I'm losing a neutron, I'm gaining a proton. So when I look at that N over Z ratio, I'm losing a neutron, N goes down, Z goes up. So this ratio gets smaller. That make sense? So if you had to answer this question on an exam, if I had to answer this question on an exam, which, standing up here kind of feels like an exam sometimes, because I ran out of time to actually look over this stuff before class. So I'm just thinking through, right? So before I go and look at this, I'm going to reason this out and make little notes for myself so that I can go over there and get the correct answer. Writing notes like this that you bring in your head isn't cheating. It's you brought the knowledge in, you're just putting it down so you can see it before you lose your mind, right? So the positron, let's try to keep them separate because they'll annihilate each other if they get together. So if we get a positron being emitted, the neutron turned into a proton, this is the opposite thing happening. So if we have 1 and 0 and 1 and 1, proton turning into a neutron. Yeah. So this means that the N to Z ratio will go up. Make sense? So what we're going to do is we're going to look at lead 192. So we need to find lead on the periodic table and see what is the atomic mass of lead. The average atomic mass of lead is 207.2. So lead 192 has lower mass than a stable nucleus. Right? The stable one is probably lead 207. So how is this going to become stable? I'm hearing both. And my brain is not working. Brain's not working. So let's look at it this way. So lead has 82 protons. So we could do the minus 82 is 110, right? Is that right? 110 neutrons. So we can actually calculate this ratio here. 110 neutrons over 82 protons. That's a 1.34. And then we can calculate it for this stable, call it 207, right? 207 minus 82. (125 neutrons). 125 neutrons over 82 protons. (1.52). This is the stable one. This is the unstable. So we need this ratio to go up. It's going to be positron emission. Does that make sense? This is the long, slow way, but it gets the right answer every time. I like that. Let's look at lead 212. Let's actually go back and look at this and see if we can find a shorter way than doing it like this. So this mass number is lower than the mass of the stable one. And so we want this to change in a way where the mass number goes up. Not the number of protons, but the mass. And so we need more neutrons. And so that's going to be positron emission. Here we have 212. This is still lead. The stable is 207. So we need this to come down. So this is going to be beta decay. So this first one was positron. And this one's beta decay. And we could calculate the ratio if we wanted to. 212 minus 82. (130). 130 over 82. 1.59. So to be closer to the stable isotope, we need this ratio to come down. Beta decay decreases the ratio. Any questions? Let's try xenon 114. So we look at the periodic table, and the average atomic mass for xenon is 131.294 atomic mass units. So the mass number here is smaller than the mass number of the stable isotope. So we need to do something that's going to increase the mass, but we don't want to change the number of protons. So we want positron emission. Does that mean that that's what that isotope's going to do? No. But that's probably what it's going to do. Any questions? Magic numbers. So it turns out the actual number of protons and neutrons also has an effect on the stability of the nucleus, not just the ratio, but the actual number. Just sort of a fun fact. Large number of stable nuclides have both an even number of protons and an even number of neutrons. Why? I don't know. It just is. It's kind of cool, though. Even protons, even neutrons, much more likely to be stable. So if we look at stable nuclides, 157 of them have even protons and even number of neutrons. Only 5 stable nuclides have an odd number of protons and an odd number of electrons. Just kind of funny. So the theory on this is that the nucleons have a tendency to pair together, much like the electrons do. You get these spin-paired electrons. And so when you have even numbers of protons or even numbers of neutrons, they can pair up like that. So we've got energy levels within the nucleus, and we find that atoms with certain numbers of electrons are uniquely stable. See the noble gases. And we see that atoms containing a magic number of protons or neutrons are also uniquely stable. So if you have the number of neutrons or the number of protons equal to 2, 8, 20, 28, 50, or 82, we're especially stable. Or if you have the number of neutrons being 126. Notice that all of those numbers are even. Those are the magic numbers. I do not expect you to remember the magic numbers. We should have an understanding of the concept, but you don't need to memorize those. I wonder what would happen if you played those in the lottery. I wouldn't recommend that. I'm sure someone's done it. And I'm sure there would be at least one time in all of history where that would win you something. But that's true of any combination problem. Okay, so atoms above number 83 are radioactive. All of them. They don't have any stable nuclides. They're all radioactive. They're going to decay. They may decay in one step or in more than one step. Mostly it's alpha and beta decay. Gamma decay also occurs with some of that, just removing excess energy. And the decay will continue until you hit a stable isotope. When you get a stable nuclide, it's stable and it's going to stop. So this is what happens with uranium-238. So we've got alpha decay to thorium-234. Then we have beta decay to, I think that's protactinium-234. Beta decay back to uranium-234. Alpha decay to thorium. Alpha decay to radium, radon, polonium. And then it can go two different ways. You could go to lead or to acetine, and then to bismuth. And then again, there's two different options, polonium, or I think that's thallium, lead, bismuth, polonium, or thallium, and eventually at lead 206. Every arrow there, you're having alpha particles or beta particles shooting out, and possibly gamma rays as well. So, Henri Becquerel, experimenting with those uranium-containing crystals, probably was exposed to a significant amount of radiation because all uranium atoms are unstable.